My thanks to the IAVM for inviting me to give this presentation on osculation. This has very many beautiful and powerful applications, and I'm just going to give an outline here so there won't be any proofs involved, just the applications themselves. So let's start with Teertj's method for divisibility testing, where he introduces the idea of osculation. Suppose you want to divide this number by 19. We first of all select our osculator, P1 is 2, and 2 because 1 more than 1 is 2. And we use 2 as a multiplier. We multiply the last digit, the 8 here, by 2 and add on the previous digits. So 2 8s are 16 and 1 is 17. Then we can multiply the 17 by 2 and add on the 3, but it's easier if you just carry this 1 over to the 3 and only multiply the 7 by the 2. So we get 14 and 1 is 15 and 3 is 18. And then again, 2 times 8 is 16, 1 is 17 and 2 is 19. And because we've arrived at the divisor, we can say that this number is divisible by 19. We can actually reduce any of these numbers by 19 as we go along to stop them building up. So I could replace that 18 with a -1 or that 17 with a -2. Anyway, this is just the first osculator, and this table shows the oscullators. So there's the first osculator, P1 is 2, which means 19. And to get the next osculator, we just keep multiplying by that initial 2. So to get the next osculator, osculate by P1. So 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, and when we take away the 19, we get 13. Oscullators are always less than the divisor. An easier way that Teertj shows us to get that 13 is to just multiply the 6 by 2 and then add on the 1. 6 2s are 12 and 1 is 13. So here we can say 2 3s are 6 and 1 is 7 to get the next osculator. Then 2 7s are 14. So those are the positive oscullators, and there are also the negative oscullators. This 4 here represents the number 399. The 2 tells you that there are 2 9s, that it's based on hundreds, and it's 1 less than 400. The 8 here means 1 less than 8,000, 7999, and so on. So we're going to use this 4 here. This says P2 is 4, which is there. And because our subscript is 2, we're working in hundreds, we have to divide the number like this now, separating 2 digits on the right-hand side. So we proceed as before, but we're multiplying 4 by 18 now and adding on the 23. 4 18s are 72 and the 23 is 95, which you may recognize as being 5 19s. If you don't, you can go back here and use P1 is 2, multiply 2 by the 5, which is 10, and add on the 9, you get 19. So that's just a brief introduction, what Teertj shows us. And here we've got d equals 7, different table. So we start off with 5 this time, and that's because the first multiple of 7 that ends in a 9 is 49, and 1 more than 4 is 5. And again, we can osculate by P1 to get the next osculator. So we'd say 5 times 5 is 25, and when we throw out 3 7s, we're left with 4. Then 5 times 4 is 20, which becomes 6 when we cast out 2 7s. And so on. We keep multiplying by 5, we get all the positive osculators. And that's the full cycle in this case. There are 6. Cycles, they go on forever to the right and to the left, and in a block of digits that keeps repeating. So these 6 numbers keep repeating in that cycle. Now the negative osculators, the first one is 2. The negative osculators all represent numbers that end in a 1, or zeros and 1. So the first multiple of 7 that ends in a 1 is 21. So that's where the 2 comes from. And again, we can oscillate by P1 to get the next negative oscillator. So 5 times 2 is 10, but we throw out a 7 and we're left with 3. And that's the number 301. If we multiply again, 5 3s are 15, and we throw out 2 7s, we get 1. So 1001 is the number referred to, and we could say Q3 equals 1 for this number. And continuing, we do this. Also, you may already know that P plus Q is D, and that helps us to fill in the table if we need to do that. And this is the table for 19 that we just saw. This is the full cycle of 18 oscillators, and you can see that the columns add up to 19 this time. In fact, we can oscillate from left to right as well as from right to left. I'd like to just show you that here. So these are the two tables we've had, and we know that that 5 there generated all the other oscillators by multiplying by 5. So these are all powers of 5 from the left. Just as over here, these are powers of 2 from the left. If we oscillate from right to left, though, we have powers of 10 always. It doesn't depend on the first oscillator. So this is 10 to the power 0. This is 10 to the power 1. That's 10, because if you take away 7 from 10, you get 3. If you divide 100 by 7, the remainder is 2. So that's where that 2 comes from. Same over here. We start with a 1, which is 10 to the 0. Then we have 10. Then we have 100. But if you throw out 19s from that 100, you're left with 5. So this diagram summarizes this. We've got powers of P1 from left to right, and we've got powers of 10 from right to left. Here you'll see the numbering is changed at the top, because these oscillators deserve to have their own notation, which I'm calling R and S. So we can say R1 is 10, R2 is 5, and S3 is 7, and so on. And to show how we might use this, oscillating from left to right instead of right to left, we'll take this example from before. And it's divided into two numbers here because I'm going to use that 5. R2 is 5, and that subscript is 2, so we've got 2 digits separated on the right. So instead of multiplying the last digits and adding on the previous, I'm going to start at the other end and multiply 5 by the 23 and add on the 18. 5 times 23 is 115, and with the 18 we get 133. Now it may not be obvious that that's a multiple of 19, but we can repeat. We can split 1 and 33 apart and multiply the 5 by the 1 and add on the 33 to get 38, which is a multiple of 19. So this is quite nice, and actually it has advantages over the right to left oscillation because it always gives the remainder. The final result is the remainder, which is very useful in factorization. So let's look at factorization and how we might do that by easy Vedic methods. Suppose you want to factorize this number. The usual way would be to test for divisibility of all the prime numbers up to the square root of the number. But that would be quite a lot of work. So we want a better method. Suppose we want to use the number 1001, which happens to have these factors, 7, 11 and 13. And also it can be represented by this osculation equation, Q3 is 1. We just saw that for D equals 7. But because of the different way of applying negative osculation, which can be a bit awkward, I always like to use the positive equivalent. So I'm going to use P3 as minus 1. I've just changed the 1 to a minus 1. So you would osculate by that. I'm going to do this from right to left. Because we've got a 3 here, I'm going to split this up like this, separate 3 figures on the right, and then multiply the last group by -1 and add on 4. Minus 81 and 4 is minus 77. Now, because 7 and 11 are factors of 1001, they must also be factors of this number. And 13 is not. So we can say that 4081 is 7 times 11 times some other number, and we can use another of these special numbers like 1001 to get that 53, or we can simply divide 77 into 4081 using reverse vertically and crosswise multiplication. So you'd say, this must be a 3 because 7 times 3 has to end in a 1, and this must be a 5 because 5 times 7 has to come to about 40, just under it. Anyway, there's a simplification of this, because if we're only doing one osculation, which you've done here, we can do it like this. There's our 4081, and our 1001 is written like this underneath. This is 1001. Now we just cross multiply and subtract. 81 take away 4 is 77. That's it. So it's just mental mathematics. Let's just apply this to this number here. We'll use the same number again, 1001. So 1001 means we put, well, first of all split it apart like that, and then put the ones underneath, cross multiply and subtract. 61 take away 35 is 26. Well, we've only got one factor, so we could try another special number. What about this one? We can test for divisibility by these three factors in the same way. Because it's thousands, we separate three figures like that, and this time we got 2001. We cross multiply and subtract. We get 122 minus 35, which is 87, which is 3 times 29. So because they're both factors of 2001, they're also factors of our given number, and 23 is not. So far we've got this number is 3 times 13 times 29. There's also a 31 there. To get the 31 we can divide as we did before, or we can use more special numbers. What about this one? It's got 31 as a factor, so this should work. Of course you don't know that when you start. So there we are, there's our number, and this is 4000 minus 1, our number here, our special number. Cross multiply and subtract, we get 279, which is 9 times 31. That proves that 31 is a factor of our number. Or if you want to use 403, convenient because it's got 31 as a factor, and then you'd have to split off 2 digits on the right because we're with hundreds here, and you put in your 43 there. I'll leave you to check that when you cross multiply and subtract, you get a factor of 31 in the number. Now some other applications of left to right osculation, changing this number into base 10. Let me just spread the numbers out a bit first. So we're simply going to osculate from left to right with this 5. 5 times 1 is 5 and 2 is 7. 5 times 7 is 35 and 4 is 39. 5 times 39 is 195, with the 3 is 198. So there's the answer, 198. We could also go the other way and change base 10 numbers to another base. And this is also useful for checking calculations and factorizing polynomials. Substitution. If we want to find the value of this cubic when x is 2, we simply osculate from left to right. So we start with the 2. 2 times 2 is 4 and 7 is 11. 2 times 11 is 22 and 9 is 31. 2 times 31 is 62 and 3 is 65. So 65 is the value of the cubic when x is 2. We can also do divisions very easily. If you want to divide this quadratic by x minus 3, 3 is the number that brings this to 0, so we're going to osculate with 3 from left to right. So we start with the 1, then 3 times 1 is 3 and 5 is 8. 8 times 3 is 24 and 7 is 31. So the answer to the division is actually x plus 8, remainder 31. One last example, factorizing this cubic. Looking for a factor of the last term there, we could try x equals 1. So I'm going to osculate with 1, see if I get a 0. Start with the 3. 1 times 3 is 3, minus 4 is minus 1. 1 times minus 1 is minus 1, plus 3 is 2. 1 times 2 is 2, minus 2 is 0. So this shows x minus 1 is a factor of that cubic, but also gives the coefficients of the quadratic quotient. So this is the factorization of that cubic. So thank you very much.